objective that you covered when you were in exponential algebra. We want to model exponential growth and decay. It's just a matter of reminding you about this before you take the MCAs. Speaking of the MCAs, by the way, a couple of people have gone through that practice online one because they changed the settings, so you can now get to it on your Chromebook, juniors. A couple of things. Make sure you bring your own calculator, but if you forget, remember that the graphing calculator is going to pop up, but here's the deal. Their graphing calculator is always going to pop up in radians mode, and we know that that's not what we use for the trig. So if you have to use the pop-up calculator, you're going to have to go under mode and change it to degrees. So if you forget your calculator, remember to change that. The other thing is, apparently, if you do a probability problem and you say, okay, it's the probability of tossing a coin and getting hits, and you try to put in 50%, it will take it, but it will say that it's wrong because it only takes mathematical numbers. So it wants 0.5 or 1/2. It would accept both of those, but it will not take 50%. So if you're doing probability, just remember, always give it as a decimal or a fraction, and you'll be okay. All right, I know that was a little off, but I'm going to remind you about that again because I can't remind anybody on test day. We're not allowed to do that. So on test day, we have to clear your memories and basically say, here you go, it's all you, you know. So I'll try and remind you again on Friday. We're going to model exponential growth and decay, but what we're not going to do because it's going to take too much time is this little getting ready thing here. We're going to go right down and get busy here. Graphing an exponential function, we'd want the most basic exponential function that we could get. And if we want to talk about growth, we know we need a number bigger than 1. So the easiest one to pick would just be a 2. You know, we don't want to work with 1.1, 1.2, or anything like that. We just go to the next integer, which would be a 2. And what we do if we don't know how to graph something is we always make a table to get an idea of what's going on. So if we had 2 to the negative 4, that would mean we're going to have to flip it and make it 1 over 2 to the 4th. Well, everybody's memorized 2 to the 3rd is 8. So 2 to the 4th is 16. This is going to be 1/16. And you could sure put that in your calculator and get it as a decimal too if you wanted to. So to the negative 3rd power would be 1 over 2 to the 3rd, which, like I said, we've memorized that dealing with all the power that we did before. And then 2 to the negative 2, 1 over 2 squared, which would be 1/4. 2 to the negative 1, 1/2. And then anything to the 0 power is 1. 2 to the 1st is 2. 2 squared is 4, and it looks like I'm going to have to scroll up a little bit here. 2 to the 3rd is 8. So, graphing 1/16, it's going to be tough. You know, I know in your packet, those little grids are very, very small, and it's hard on the smartboard here, but we need to go to negative 4 and just a little bit above 0, just a little bit. And then negative 3 1/8. And then we have negative 2 1/4, so starting to get a little bit higher. And negative 1 1/2, 0 1, 1 2, 2 4, and 3 8. Now this is a really good example of what we talked about when we were trying to find the sum of infinite geometric series. You know, because what we'd see here is as we're going back to the left, we're getting closer and closer to 0, but we're never quite getting there. And that's why it approaches the x-axis as a limit. And that makes this what's called an asymptote. It's never going to get to the x-axis, but it's going to get seriously close. So close that the human eye can't tell the difference. But our graph shows us growth as we go from left to right. And we want to make sure that our graph doesn't look like it crosses that asymptote. We know it's not supposed to. Mine really shouldn't be looking like it's going back up either. It should stay kind of flat as we go there, but you have to be careful with those asymptotes. So here the x-axis, which is the line y equals 0, is our asymptote. So I started thinking ahead about, well, what could change that asymptote? You know, I know h and k are coming. They have to. It's just, they come together, graphing and h and k. So if I were to move it right or left, that's not going to change the asymptote. You know, obviously, changing the asymptote has to do with up and down. So k will affect where that asymptote is at, but not h. Not going to have anything to do with it. So there's our basic growth right there. Well, this is 2 to the x, the most basic graph that we can get that deals with growth. So what happens if we have to graph like 4 to the x? Well, because of the work that we've already done with powers, we know this is going to go up faster. But you know, how much faster? Let's take a quick peek. And I'm not doing all of those numbers that they did. Here's why. 4 to the x is growth. I already know that on the left-hand side of this graph, it's going to approach the x-axis as an asymptote. So I don't need many negatives for this one. I'll maybe just do 4 numbers there. -1, 0, 1, and 2. I just want to see how fast it's growing. So to the -1 power, 4 would be 1/4. And again, I know what it's doing on that side. In fact, in quadrant 2, it's approaching the x-axis. Anything to the 0 power is 1. 4 to the first is 4, and then we're already off our grid there. But it gives us something to point at, you know, when we make our graph. So let's go down and put this one on here at -1, 1/4. And yeah, they got super teeny. At all? Oh man, so another batch of bad copies. Oh no, no. All right, so just kind of guesstimate. You know, we'll do the best we can on these and kind of call them sketches. 2, 3, 4. They're too light. 16 would be somewhere up there. So it's going up faster. You know, we can see that in the last graph, after we put a 1 in, it went up really fast. And it's kind of the same thing here. It's not that it's not going up fast from 0 to 1, but it's definitely going up faster as we go from 2 to 3. And that's one of the things you look at when you get to calculus is, okay, what's happening? You know, just from x equals 1 to 2, how fast is this going on? And that's slow. And then you look at, well, what's going on from 2 to 3? How do I see that? How do I compare that? Then the next one changes big time. That's not growth. That's decay. That's a number between 0 and 1. So this shouldn't go up as we go from left to right. It should start high and go down. So that means I probably want a few more numbers in the negative zone. You know, maybe in -2, -1, 0, 1, and 2 might be good. Just so that I can see on the left-hand side, this is starting high. So with a -2, we'd take a 1/3 and we'd have to flip it. And that would give us 3 squared. Which, yeah, shows us it's starting high. You know, as you graph this one from left to right. To the -1 power is going to flip our little 1/3 and give us a 3. Anything to the 0 power is 1. To the first power will be 1/3, and then 1/3 times 1/3 would be 1/9. And yeah, we already knew that was going to happen. You know, this is a backwards graph because it's a fraction between 0 and 1. Bless you. So -2, 9. Again, do the best you can. That there must have been a bad cartridge or something. She was copying these off. We can definitely see the difference. It is the same thing we talked about when we were talking about sequences and series. You know, it's geometric, and you see an R value between 0 and 1, that's decay. This is going down. So this is, you go to the doctor because you're sick, they say you have strep, your bacteria is way up here in the petri dish. But you take your antibiotics for a couple of days, and slowly but surely that bad bacteria starts to get killed off. You know, it just does. Speaking of illnesses, Eli. All right, y equals 2 times 3 to the x. We were talking about bacteria. 2 times 3 to the x, growth or decay? It is growth. So I probably don't need a whole lot of negatives. Maybe -1, 0, 1, 2. And it has a 3, so it should go up pretty fast for the power. But then there's also a 2 in front. So yeah, this is going to go up pretty fast. So if we have the -1 up here, that's going to be 2 times the flip, the reciprocal of 1/3. So that will give us 2/3. But of course we see it's a fraction. And we know that's going to be low on the left-hand side. And then to the 0 power, 3 to the 0 is 1, so we'll get a 2. And I think back and I realize this could really be described by a number out front, this 0 piece. But there isn't a number out in front of this one. So what number would it be? It would be a 1, exactly. So 0, 1 makes sense. It's going through 0A. 0, 1 on this one would make sense. Little imaginary 1s in front of that power, just like when we had geometric rules. If there wasn't one out in front, it was a sub 1. Now if we put a 1 in this little bugger, we've got 6, and a 2 in there is 18. It's shooting up pretty fast. So let's get that one graphed. So not only was that growth because of the 3, but we also had to multiply it by the negative 2. Somewhere up there. Yeah, it's going up big time, right? I missed my little for the negative 1 there, but we know that that's what it's going to be. All right, so, hey, none of these cross the x-axis. Not a 1. Because there's no k values. You know, k is 0. So when k is 0, our asymptote is always y equals 0. The x-axis, no matter what. All right, now, exponential functions model many, tons of real-life situations. Half-life, whether or not it's medications or half-life of radioactive substances. Radiometric dating, interest-bearing savings accounts, population growth, a bouncing ball. You know, we have gravity on Earth, so the ball doesn't keep bouncing forever. You know, it starts high and goes lower each time. So those are geometric relationships that can be described by exponential growth and decay. So, bless you. Exponential function, y equals a times b to the x. I'll add that little x up there. That's what makes that exponential. A is not 0, because then it would just be a horizontal line. In fact, it'd be the x-axis at y equals 0. B is greater than 0, and b is not equal to 1. 1 does not create growth, because 1 to any power is just 1. It's not going to change anything. B is a constant, and x is called the independent variable. That's the reason when we made the tables, we were always putting numbers in for x, because those are the ones we get to choose. They're independent. Now, we've got 2 situations that we saw, and that is exponential growth and exponential decay. And because of what we've already experienced in Chapter 9, we knew what to expect about which one was going to be growth and which one was going to be decay. And you also knew this from exponentials years ago. So when your b value here is greater than 1, we're going to experience growth. And like it says, a will be greater than 0 in this case. We do know that a negative in front of that graph is going to flip it below the x-axis. A, h, and k are still working the same way they've always worked before. Our exponential decay over here, and yeah, that's really weird that my little x went in the wrong spot there. I hope it's right on your packet. Okay. And a is greater than 0, but b is that fraction between 0 and 1. That creates that decay situation. So we see our well, kind of these are our parent functions for exponential growth and decay. Because if you ask somebody, pick a number bigger than 1 that would indicate growth, they're not going to say, 1.3, I really want to work with that. You know, if I've got to work with it, the next number somebody would pick would be 2. It just makes sense. And if you ask people to pick a fraction between 0 and 1, 1/2 is always the first choice. It's not like fractions are fabulous to work with, but at least 1/2 isn't horrible. So this would be our most basic growth and our most basic decay functions. And there's our little asymptote, which is a line the graph approaches as x or y increases in absolute value. So what that means is, you know, as we go to 3 forever, past 3, positive 3, 1, 2, 3, 4, where's it going? Or in the case of what we've been doing, as we get closer and closer to the x-axis, it's getting closer and closer to 0. That's our asymptote. Never going to quite get there, but we know 1 over 256, it's even really hard to draw that, to look at it on your fingers and say 1 over 256. So it's so close to 0, it's not mathematically significant anymore. Our y-intercept, to find y-intercepts, you always put a 0 in for x. And what we saw, if it'll scroll back for me there, is 0a so far. You know, like I said, so far. We don't have any H or K business going on. So right now, the y-intercept will be 0a. Our domain, we don't have any x's we can't put in there. We didn't experience a time when I said, let's use this number, and we went, oh, can't do that. Now there's no division here. There's no square roots, so no restrictions on the domain. But we don't get all y's back. We didn't use anything below the x-axis. So our range for these was y is greater than 0, because in fact it couldn't come out to 0. It would get super close, but not quite there. So now, in real life, a lot of this is used for savings accounts, that kind of stuff. So if you have an increase by a fixed percent each time period, that's going to be a savings account, increased by a fixed percentage each time period. Or unfortunately, credit card debt, you know, that kind of thing happens. And then we do have situations where it's going to decrease by a fixed percent each time period. Have had students in the past that went on to have their own, you know, lawn business, lawn care business, and would come in and talk to me about how, hey, I get to depreciate my computer, you know, over the years. So I'm using these formulas as I'm doing my taxes each year. You know, it used to be that you could actually write off your entire computer the first year that you started your business. But now it's gone down to, okay, now you can write off half in the first year and 25% in the next year. So you keep up on the tax laws, and that will give you your decreases, which are called depreciation in taxes. So this, you guys see this one in the back? This was kind of small. Maybe I can make that bigger. Zoom.
I had 20.
150.
You know, I
You can
haven't,
see it?
I
Okay.
haven't told them that in the class.
All right. This is just a kind of a goofy font here, and I think it makes it a little difficult. A of t equals the amount after t time periods. In most cases, we're talking years, but sometimes when things are compounded quarterly, then it gets a little bit different. Little a is the initial amount. What did you start with? And then t is, of course, number of time periods. How many times is something like this going to happen? So we see two different formulas down here. One is for growth and one is for decay, and it just makes sense. This one has a plus and this one has a minus. So the growth situation, again, things like the savings account, just like the MCAs, we want to be careful that we give percentage increases as a decimal when we get those, because in math formulas, we have to have our percentages in decimals. You know?
It's not like figure 8.
That's supposed to be a percent symbol here. Yeah, it's not the best font for this. I think I should change that. Somebody else made this one last year, so I'll change to a different font. B is called the growth factor, and the growth factor is all of this. That's the growth factor. So this is how when your parents, hopefully they get something about investments that they've done for retirement. This is how businesses will occasionally try to make it sound like they're doing better than they really are. You know, because they'll say, well, look at these numbers right here. We had a growth factor of 2. And you think, okay, well, a growth factor of 2, that's really great, but it just means it's 100% better than it was the year before. It doesn't, in our minds, to most people's minds, it would be like, wow, that's huge. It's twice as much as it was before, but it really is just 100% increase. But if the growth factor is 3, then they're looking at a 200% increase. But you have to be careful about those numbers and read things carefully. And over here, R is still going to be percentage decrease, like I said, with the same thing we were talking about with the MCA. So make sure you have it as a decimal. That would be the safe way to go, or you put it in as a fraction. And B is the decay factor, 1 minus R. That means, what are you losing? Well, if you write off 25% of your computer, 1 minus 25% would actually be 75%. So it's retaining 75% of its value. It has lost 25% of its value. So understanding all of that makes you an educated consumer, which is good, you know. Identify each function or situation as an example of exponential growth or decay, and then give the y-intercept. So take a look at A, and look at what's being raised to the power. Is this one growth or decay? This one's decay, yeah, because this is less than a 1 for 100%. So this is decay. And it said, what is the y-intercept? It's always 0, A. So what's A? 12. There it is. Take a look at B. Growth or decay? Growth. 0 what? 0.25. There it is. You put $1,000 into a college savings account for 4 years, the account pays 5% interest annually. Would that be growth or decay? It would be growth. You're hoping it's growth anyway, right? It is growth. And then 0A in word problems doesn't make a lot of sense, but 0A is, what did you start with? How much money did you put in? 1,000. And our lowercase a always stands for initial amount, which is what did you start with? So there it is. All right, another got it. I think we can just go through this one pretty quick here. Growth or decay? Y-intercept. A. Growth. 0 what?
3.
B. Growth or decay?
Decay.
0 what?
11.
2,000 bucks in a college savings account for 4 years. The account pays 6% interest annually. Growth.
2,000.
Just being able to tell the difference between those two. But on the MCAs, they do something different. They go into a little more detail. And that detail is, do you recognize how much growth or decay has taken place? So we're going to identify these as growth or decay, but we're also going to give the percentage of growth or decay as we go through this. So take a look at number 1, growth or decay. Decay. Now, thinking in percentages is a lot like thinking in terms of money, where $1 is 100%. So if this is down to 34 cents, how much did it lose?
66%. I don't know how to subtract. That's a lot to subtract.
Well, you can always use a calculator. All right, take a look at 2. Growth. Growth. Think money. How much over $1 have we got there? 5% over. So you've got a nickel over $1. So 5% growth. Number 3, growth or decay? Growth. Percentage increase? Oh, careful.
6.75.
Good. Yeah. So we have a lot more numbers to keep track of there. So you recognize that they're adding 0.0675 and you say, okay, as a percentage, that would be 6.75%. Number 4, growth or decay?
Okay, 40%.
60 cents. 40% lost. Number 5, growth or decay? Yeah, most of us would grab a calculator for that one, right? So we've got our 1 for 100%. So as a percentage,
97.875.
lost a lot of its value. Lost a lot. Number 6, growth or decay? Growth. How much as a percentage? 200%. 200%. Absolutely did. Number 7, growth. How much growth as a percentage?
7.
That percentage label is important to everybody, because if you don't put the percentage label on there, then it's wrong. Because the decimal equivalent would actually be 0.875. All right, look at 8, growth or decay? Decay. 98% decay.
Thanks, Joe. Yeah. Yeah.
There we
Let's
go.
hear it. Let's hear it.
All right. So, modeling this growth, making sure we understand how do you find all of this
We
stuff.
heard it.
And it says you invest $1,000 in a savings account at the end of 6th grade. The account pays 5% annual interest. How much money will be in the account after 6 years? Growth or decay? So our little growth model for our word problems was just that. Not a lot to it, which is good. And what we have to put in is A and R and maybe T. But for the model, we at least need A and R. So initial amount, what did you put in originally? 1,000 smackers. What did it pay for interest? Okay, yes, 0.05, because remember, when we put it into a math formula, it gotta look like that. We could pretty it up a little bit. We know that $1 plus 5 cents is $1.05. So this would be the model that we would use. If they say, write a model for blah, 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 that's our nice little simplified model, right? But they do want us to take this one a little further. It said, how much is going to be in the account after 6 years? So where do you suppose the 6 goes? T. And then we grab a calculator because nobody makes friends with decimals. We just don't. $1,340 and see, the bank is usually just going to give you $1,340.09. They don't usually round up because they're a bank and that's how they make money. But we're going to go ahead and round and say $1,340.10. Unless you're a super cute little kid, then they'll give you the 10 cents. They'll say, well, it's so close to 10. We'll give it to you. Because they want your business in the future. So if you're a youngin' and you're coming in, they want your business for the rest of your life. All right, the populations of 3 neighboring towns and their growth or decay rates are listed below. Ta-da! Find the population after 10 years. Oh, okay. Well, Cedarville has some growth. So we're going to use that one. Let's see. Starting at 47,162, and we'll do what's in the parentheses in our noggin this time. We'd have 1 plus 0.02, so 1.02 to the T, and they want to know after 10 years. So that means we have to put a 10 in there. And see what we get. 47,162 times 1.02 10 power. And this is people. So 57,490. People. My 7 didn't show up nice there. Alrighty. Uh-oh. Peter's land is experiencing some decay. So that's going to be y equals a times 1 minus r to the t. 39,650. Anybody punch that one in yet? 1 minus 0.031. Oops, don't need that parenthesis. 0.969. And we want it to the 10th, but for the model, we'll just put a T right there. So let's see, 39,650 times 0.969 to the 28,939 people. Ooh, they're going to be hurting. Look at that. They're losing more than 10,000 people.
This is a higher population.
Yeah?
Yeah.
Oh, what's up? McD City, growth.
Oh,
So 58,975. 2.3 per 3. I'm having a hard time getting the 5 out. 2.35% growth. So 1 plus 0.0235 to to the t with a 10 in there. 5,975 times 1.0235 to the 10 power. 74,395. Peoples. Growing.
Big eventually.
You know, Elk River is back in the news again as one of the most extreme growth populations in the state. It's just a growing suburb. So, how do you plan for that stuff? Well, you hire a good city planner and you have some good mathematical models, because there are certain things you have to keep track of, and that's like water towers. You know, a water tower only services so many people. So once you reach a certain population, you're going to have to pay big bucks to put in a new water tower. So those things need to be planned for. So we want to know when the population of Cedarville is going to reach 65,000. Well, we had a model for that, didn't we? Y equals 47,162 times 1.02 to the t. Where do you suppose 65,000 is supposed to go? It is, that's not time. We would love to be able to solve this by hand. But we can't learn logarithms until after the MCAs. So, we're going to use our graphing calculator. We're going to have to figure out where these two things hit each other, which means I should get a couple of your graphing calculators. I should have done that earlier. We have no choice. We don't know log. Have any of you done logarithms in your science class? Okay, good. So a few people that have experience with logarithms, because what we would do with logarithms is we'd divide both sides by 47,162 and then we'd use logarithms. Others? Sorry, you asked.
We're gonna have to do this before.
You will. That one? Alrighty. So here's what we're going to do, which is, you know, what you'll experience on the MCAs for this too occasionally. We're just going to do the y sub 1, y sub 2, and let Blinky give us the answer.
Come on, Blinky.
Blinky's been laid off for a little while, so Blinky's happy to see some work.
I thought you were retired.
It's my pet cursor, Blinky.
Blinky retired.
And he's coming back to work.
Coming out of
He's
retirement.
decided coming out of retirement for a little while.
Yeah, it's way off the charts.
So we're gonna have to do something about the window here. So window, let's see. When will it reach 65,000? Well, let's see. We did 10 years, and it was at 57,490. Do you think 30 years enough? 30. And we have to be able to see 65,000. So on the y's, I think I'll go 70,000. Let's see. Come on, intersection. Yes.
That away, Blinky.
So second trace, number 5. Bing, bang. Oh, there's Blinky. Sometime after 16 years, about 16.2 years to get there. Now, water towers cost a lot of money. Got to be some saving going on between now and then, and you know, getting some contracts. Maybe it'd be better to put it in now. But most places would say, no, you know, that's too far out. 16.2 years. There's a lot that could happen to our growth between now and then. So we'll save for it, but we're going to kind of watch what happens with the population and see whether or not it continues to grow like it is. Then we have another good word problem here, and this is about Iberian links. It says exponential functions are often discrete. That means countable. So we really can't be, we shouldn't be connecting up these graphs. These graphs should just be dots, because you can't have 3/4 of an Iberian links. It doesn't work that way. You have one or you don't have one. So to model a discrete situation using an exponential function in that form that we have, y equals a times b to the x, we have to figure out a growth or decay factor. And if we know y values for 2 consecutive x values, you can find the rate of change and then find b using this formula for rate of change. Rate of change is just slope. Whenever I taught exponential, I always had students memorize slope, slope, find the slope, average rate of change. y2 minus y1 over x2 minus x1. It is just slope. The only difference is, instead of looking at both x's, all we do is divide by the first value. So y2 minus y1, what was the change, and how does that compare with what it was originally? Average rate of change is slope. They don't ask you for slope on the MCAs, they ask you for average rate of change. It is the same thing. So here's the poor little Iberian lynx. The table shows the world population of the Iberian lynx in 2003 and 2004. It's not looking good for the Iberian lynx. If this trend continues and the population is decreasing exponentially, which it was, how many Iberian lynx would there be in 2014? So we're going to use our y equals a times b to the x, but we're also kind of thinking in terms of, this is a word problem, so it might be better to use y equals a times 1 plus r to the x. Not going to worry about the whole define the variables thing. What I want to know is, what should I use here as far as a slope goes, because that's what I need for r. I need the slope. So what happened here was the change in y values was from 150 to 120. So 120 minus 150 divided by what it was originally, which was 150. And that will get me my slope. And that is going to be a negative 30 over 150, which we actually could make a really nice negative 1/5. But the book tends to go with decimals whenever you're dealing with any kind of word problem situation. So either a negative 1/5 or negative 0.2. That's bad news for the lynx. And it's definitely going down. And it's going down by 20%. That is not good. So now we put this into our formula. And if you're wondering, why did they choose that formula? Why did they say use the growth formula when this is decay? Because our slope comes out negative. So we want to use something that's going to give us an accurate representation. It started with 150. 1 plus a negative 0.02 would be 0.80. And the good news is they were keeping 80% of the population each year. Bad news is they're losing 20%. And you can only go so low with something like an Iberian lynx. So there's our model. And we wanted to know, what was it, in 2014? Yep, that's what we wanted to know. So here's our model. And we want to know 2014. But we really used 2003 as the first data. So 2014 minus 2003 would give us 11 years for T. There's an 11-year time change there. So if this had stayed, bless you, my goodness, there's a lot of dust in here this morning, or people are having trouble with their allergies. We've got 150 times 0.8 to the 11th power. Oops, too many points. Bad news for the lynx. Only approximately 13 lynx would have been left in 2014. Oh, because it's just a model. You're right. You know, it really, they're probably looking at 12 if this trend had continued. But because it's just a model, you know, you go a little on the hopeful side here and say, it could be 13 full lengths, you know, and it could be at this point. Now, the got it continues this further, and it says, okay, what if this trend kept going? When would the population, or it says, what would the population be in 2020?
No, it's 6.5.
So how many years from 2020 to 2003? 17 years. And we're thinking this is really bad news for the links, right? So find for me about how many links.
None.
Can't have a negative amount of links. 3. 3 links. Which would probably mean the end of the links because it's kind of like, anybody in here have a German Shepherd?
Yeah.
German Shepherds, fabulous animals, but there's been way too much inbreeding over the years. And so they, now a lot of them tend to have hip problems because genetically it started off as a small problem, but because they're running out of new lines of German Shepherd blood, you know, it just is going to happen that they have hip problems. So it's rare that you can find a German Shepherd that doesn't have some kind of hip problem. Good news, I look every year and check on the Iberian lynx. There are over 400 of them. What had happened, and this is from Spain, what had happened was people were killing off all the rabbits. Well, Iberian lynx eat rabbits. So when all the rabbits were dead, the Iberian lynx started to die off. So they went back and introduced rabbits to the habitat, and they're getting back. They're getting back. So it's a good thing. And yeah, what we just said about B was, is it ever going to cross the x-axis? The answer is absolutely not. You know, they'd all be dead, and we would have 0. That would be it. So they would all be dead at 0. 0. So, like I said, I check on them every year. Kind of interesting in the news every once in a while. You'll hear stuff about extinction and all that good stuff. Oh, you know what? First, 43210. How do you feel about exponential growth rate that we talked about today? I know. You're looking good. The dodo bird. They thought it was extinct for many, many years, but they believe they have found a dodo bird.
Oh,
Still a dodo bird.
no! This changed my whole entire outlook on the world. Oh.
Well, it does, because that means stupid is back. Because the whole reason the dodos died is because they were stupid.
Yeah, they were.
Stupid is back, everybody!
Why do they think they found a dodo bird?
Well, they're putting motion sensor cameras out in places like the rainforest. And they believe, you know, it's one of those, nobody was there to see it, but they caught a bird on camera that looks a lot like the dodo bird.
Only if the woolly mammoth came back.
That would be a big deal.
You know, they should get genetically modified somehow.
They found it.
They can create the DNA of